Right now, it feels like the entire tech industry is totally obsessed with just one thing: making AI smarter. Making the models bigger, giving them more parameters, and training them to pass increasingly ridiculous, complex exams. But what if we're completely missing the other half of the equation? In this explainer, we're going to unpack a really fascinating lecture from Professor Yu Su of Ohio State University, who's also the CEO of Neocognition. He argues that we actually need to shift our focus away from scaling AI intelligence and move towards scaling AI expertise. Now, I know that sounds like a super subtle difference, but as you'll see, confusing those two things is exactly why our absolute most advanced AI still completely falls apart when you ask it to do just everyday, normal digital tasks.
Okay, let's actually kick things off with a pretty wild number. To put this in perspective, in just under 2 years, Anthropic saw a staggering 400x revenue growth. But here's the thing. That explosive growth wasn't driven by general-purpose assistants that say book your flights or manage your crazy email inbox. No, it was largely driven by highly successful coding agents. AI models absolutely excel at writing, debugging, and analyzing code. And if you think about it, coding is actually the perfect first mass market for these models. Code is already a language-native world. It's super structured, it's symbolic. And most importantly, software tests act as immediate, automatic rewards for the AI. It's essentially the ultimate playground for a language model.
But the second we leave that highly privileged, strictly governed world of code, well, things get incredibly messy. Outside of programming, these exact same frontier models, the ones that can literally ace the bar exam and write complex algorithms, start making the most incredibly silly, brittle errors in basic digital tasks. They get totally lost in drop-down menus, they completely misunderstand enterprise software, and they fail at basic web navigation. Honestly, we've all been frustrated by our company's clunky HR portal, but for an AI that can ace the bar exam, it raises a really crucial question for us. How on earth can an AI be so incredibly smart, but so brittle the moment it has to do standard office work?
To really understand why they're so brittle, we have to take a quick look at the history of AI agents because, we aren't exactly doing this for the first time. Back in the 1960s to the 1980s, we built expert systems and logical agents, but they were strictly limited to rigid logical reasoning. Then, jump to the 2010s and we got deep reinforcement learning agents. That's essentially AI learning by trial and error, but they usually only excelled in single-modality tasks, like dominating a specific video game. The present day, though, it's an entirely different ballgame. With multimodal language agents, we finally have neural models that can unify multisensory inputs into one single representation. So for the first time ever, AI can combine seeing, reading, and symbolic reasoning, which drastically improves how adaptable they are.
And yet, despite this massive evolutionary leap, industry leaders are actually tempering their expectations. Andrew Ng recently made a great point. He noted that it's not going to be the year of agents, but rather the decade of agents. Why? Because right now they fundamentally lack reliable computer use and continual learning. You can't just drop an AI into a messy enterprise setting and expect it to learn on the job. Sure, they are incredibly powerful right out of the box, but their inability to adapt over time means they just can't function as reliable digital workers yet.
So what we're essentially witnessing here is a modern version of Moravec's paradox. The original paradox basically said that high-level reasoning takes very little computation, but low-level physical skills require enormous computational resources. The modern AI version is that complex symbolic reasoning like advanced math and coding, which we historically consider the absolute crown jewels of human intelligence, are actually easy for AI. Meanwhile, the easy things, like clicking through an idiosyncratic HR portal to just request a single day off, are surprisingly hard. The reason? They require entirely different cognitive competencies.
The real root of this paradox is that the digital landscape, well, it isn't just one clean, unified space. Instead, it's made up of millions of completely idiosyncratic microworlds. Every domain is different, every company is different. I mean, even if two companies use the exact same enterprise software, they're going to configure it completely differently. Each of these spaces has its own unique local physics, the unwritten rules, the weird constraints, and the hidden buttons unique to that software. It is just way too heterogeneous and chaotic for any massive monolithic foundation model to just compress into one static representation during its initial training. It's impossible.
To fix this, Professor Su proposes a massive paradigm shift, and it starts with how we define raw intelligence. The working definition for this explainer is that intelligence is the capacity to reason through unfamiliar problems from available context. And honestly, this is exactly what today's frontier models are incredibly good at. You hand them a problem statement, give them some context and some tools, and they will reason their way through it even if they are seeing it for the very first time. But crucially, in this state, the AI basically has the memory of a goldfish. Every single episode is entirely independent from the last.
Navigating those millions of chaotic microworlds we just talked about doesn't just require raw intelligence, it requires expertise. And expertise is defined as accumulated, situated competence. It's that ability to act reliably, efficiently, and with deep judgment to achieve reproducible, superior performance in one particular domain. Basically, intelligence is what you use when you have absolutely no idea what you're doing. Expertise is what you rely on when you've already done it 1,000 times before.
When we actually put these two concepts in action, a really fascinating contrast emerges. Intelligence actually expands the search space. Because the AI is just trying to figure things out on the fly, it essentially spins up all these parallel brute force attempts to find any viable solution it can. Expertise, on the other hand, immediately compresses the search space. An expert already has the learned shortcuts and understands the deep structure of the problem, so they immediately zero in on the most plausible path without wasting a ton of energy searching everywhere else.
And Professor Su considers this relationship absolutely vital. If we were to plot raw intelligence on an x-axis and expertise on a y-axis, they are largely orthogonal to each other. This means if the tech industry continues to only scale up intelligence, just making the models bigger and smarter, without figuring out how to let them accumulate specialized competence on the job, we just end up building what Professor Su calls the world's smartest novice. We get a model that is literally genius-level smart, but still brute forces its way through every single task like it's the very first time it's ever seeing it.
Because an expert is so much more than just a novice with a better memory. A seasoned expert doesn't just know more facts, they literally see the world differently. Take a really mundane task, like scheduling a meeting. A novice AI just sees it as finding an empty slot on a calendar. But an expert? They instantly recognize the deep structural patterns. They know scheduling isn't just about time, it's this complex optimization game of social authority, task priority, and urgency. Furthermore, experts understand conditionality. They know exactly when they can bend the rules for a VIP exception. They possess taste, they possess judgment, and perhaps most importantly, they know exactly when a solution is good enough so they can stop working on it.
So the big question is, how do we cross this chasm? If an AI agent is ever going to transition from just having intelligence to actually having expertise, continual learning is the critical bridge. Continual learning is defined as the adaptive compression of experience into reusable structures for future behavior. It's the core mechanism that allows an agent to actually learn from its mistakes and its successes on the job, rather than just forgetting everything the second its context window clears.
For an agent to become a true expert, it has to constantly loop through a four-step cycle. First, it gathers raw experience. Then, to make sure it doesn't run out of memory, it adaptively compresses that experience. Next up, it converts those compressed memories into reusable structures. Think of it like building a map of its specific little micro-world. And finally, it utilizes those new structures to act smarter the next time around. It is a constant, specialized learning loop.
Now, actually implementing this is a massive technical challenge, because developers have to carefully manage a core system trade-off, reliability versus plasticity. You want a system to be reliable, meaning it naturally resists change so it remains dependable and doesn't just forget its core programming. But you also desperately need plasticity, meaning it embraces change so it can adapt and learn new specialties within its microworld. To actually achieve this, engineers have to synergize parametric learning, which is kind of like permanently rewiring the AI's core brain, with non-parametric learning, which is more like giving the AI a notepad to reference later. It's actually very much like how our own human brains balance long-term core memories with rapid short-term adaptation.
So why does all of this matter so much right now? Because we have basically exhausted all the public internet data that we use to train generalized LLMs. The next massive internet-scale data opportunity lies entirely within these private micro-worlds. If we can master this in-situ continual learning, we can extract all that specialized knowledge and channel it right back to improve the general models. And more importantly, we can usher in a future where expertise becomes completely abundant. Companies are going to build automated institutional memory that forms massive competitive moats. And on a personal level, we could all have access to universally accessible expert-level healthcare advisors and tutors. By lowering the friction of learning on the job, entirely new types of digital work are going to become economically viable.
I want to leave you with a final, really provocative thought from the explainer today.
We are currently in the middle of a massive, super expensive race to build giant LLMs with higher and higher raw intelligence. But what if that's the wrong race entirely? What if, past a certain threshold of capability, we don't actually need stronger intelligence? What if the real key to the future is unlocking unbounded expertise from bounded intelligence? If continual learning gets good enough, the only thing worth scaling won't be the size of the model itself, but its ability to learn perfectly in its own little world. Something to think about.